Hi, welcome to this week's Front Seminar. Today we have one speaker. Today, Adeel Pervez will be presenting his work on neuro-differential mechanistic models. Adeel works as a postdoctoral researcher at the Institute of Science and Technology, Austria. He received his doctorate at the University of Amsterdam and master's at the University of Wisconsin-Madison. Broadly, he is interested in structural representations in neural networks as a way of encoding knowledge in neural internals. He is interested in the question, what kind of structures allow appropriate representations without sacrificing expressivity and learning? His current work develops models targeting scientific applications using neural networks with semi-symbolic differential equation representations. With this short introduction, I invite Adeel to present his work.
All right. Thank you, Vivek, for the introduction, and thanks to all the organizers for the opportunity to present my work. I apologize, my throat is a bit off today, so I'll try to speak as clearly as I possibly can. All right. So the main theme of this talk and our work that I'll present is going to be governing mechanisms and how they mesh with neural networks. So the idea is that, well, you're given some spatio-temporal data, which follows some governing mechanism. In this case, well, we have the chaotic Lorentz system, and the governing mechanism is a set of differential equations. So we're interested in the question of, given such data, how can we find such governing mechanisms? Either because we're interested in the mechanisms themselves, or we are interested in using those mechanisms for some downstream predictive task. So, the work that I present we call mechanistic neural networks. These are neural networks that explicitly model governing mechanisms in their representations. So what this means is that we impose some kind of structure on the representation in the neural network, which is sort of a prior for that network for modeling a particular class of mechanisms. So you could have any kind of mechanism, but what we have been interested in recent work is differential equations as the internal mechanisms. So, motivation why I think we should work with these mechanisms and combine them with data-driven models. So the main, I guess, reason is that mechanistic models, these are, I think, essential for reliable structured action. The problem, of course, is that machine learning models and mechanisms don't mesh that well. So, and as I said, because we're interested in how we combine differential equations with neural networks, so the sort of prior work that we're interested in is the one that combines neural networks with explicit differential equations. So this, I guess you could see three directions for this. You have physics-informed networks. You have symbolic regression, symbolic or semi-symbolic regression like SINDI, and you have neural ODEs. So all of these, in some way, explicitly combine neural networks with differential equations. There are other models such as neural operator models, but because they don't have explicit representations of differential equations, I don't include them in this list. So before going forward, I think it's useful to sort of get an overview of the differences with at least one of these architectures. I think that would provide a good handle on what we're presenting and why. So I write here for neural ODEs that this is a neural network in solver model, because basically what it does is that it takes a classical solver, and whenever the solver in its loop requires a gradient, it queries a differential equation. So it means that you have embedded the network in the solver. So this gives us two paradigms. You can either have the neural network embedded in the solver, or you can have the solver embedded in the neural network. So on the left, when you have a solver that contains a neural network, I guess paradigmatic class cases of this are neural ODEs and universal differential equations. Over here, you get accurate solvers, and you have stringent solving constraints on those solvers. What you do not get from this is differential equations are not representations in this case. So you have some data. The differential equation does not represent the data in these models. The other problem with these models is that the structure of the computation follows the computational structure of the solver, which means that if you have a solver like the Euler solver or the RK solvers, they have this outer solving loop, and the neural network is just sort of a subroutine in that loop. On the other hand, we have this paradigm of a solver within a neural network that we follow. So this allows differential equations that are representations of data, meaning that you have some data, you do a transformation, the transformation into a differential equation, and that differential equation somehow represents that data. The other thing, what we get with these is relaxed linear solving. We don't get arbitrary general purpose solvers, but we can combine these solvers with learning to model more complex differential equations. And as we'll see, these are better for learning. So this is basically our proposal. So these are mechanistic networks. This is a solver in a network model. Over here, what you get is representations that are differential equations. We have specialized solvers that natively only solve linear ODEs. However, when you combine them with learning, you can do or solve or represent nonlinear equations with basis functions or with loss terms. So the basic flow is that you have a mechanistic encoder which takes in some data, could be trajectory or spatio-temporal data. It produces the parameters that are required to specify a differential equation. So that would include, let's say, the coefficients of an equation, the initial conditions, step sizes, or whatever. So that is a representation of a differential equation representation of that data, this data X here. And then you have a specialized solver, a differentiable solver that solves this equation, produces some output, and that output you use downstream in some tasks. So this is the basic sort of the layer that you include in your bigger architecture. And then we can use these layers either, in our case, for prediction. So this would be a standard, let's say, supervised learning task. So that then this layer would provide an inductive bias for let's say, data from some field, let's say, spatio-temporal data. Or you can also use this to discover the underlying governing equations. So I'll mostly focus initially on the discovery part, and then I'll mention some prediction tasks that you can do these. So the data flow, once again, is that you describe the general form of the differential equation representations. So that is basically how many terms do you have, what order of the differential equation that you want, how many terms, what is the order of the, I guess, dimension of the system. Then you feed the data, infer the differential equation using the encoder, you solve the equation, you get a solution, you check with the ground truth and back propagate. And usually there is no direct supervision for ODE coefficient. This is unsupervised. So what is the structure of this representation? So as I said, this is a linear differential equation. However, it may be the coefficients may depend on time. So right. So you have, let's say, a dth order differential equation. You have some coefficient Ci, and let's say the right hand side B. So these are neural network outputs. So the coefficients The right-hand side, in this case, all of them are produced by neural networks given data. In addition, you can also generate and differentiate through initial conditions, step sizes, and so forth. So you would then solve the differential equation and use them downstream in some way. So in further work, what I described was for ODEs, and in our newer work, so it was published last year at ISML, or this year rather, and we extend this to PDE representations. So before we had linear ODE representations, we extend this to linear PDE representations, and then we develop linear PDE solvers, efficient solvers. So the solvers I'll describe later. But they are essential to make for making this work. So what we have, the structure of the differential equation is we have some multi-index of partial derivatives. So you have to specify which partial derivatives you're going to have in your equation, what is going to be the dimension, and then once again the coefficients will be produced by neural networks, and then you solve the PDE, you get some solution, and you use that downstream. So this is grid-based. Usually you have some differential equation on a grid. You solve it on a grid. Yeah, so that's one, I guess, limitation or feature of this. Okay, so I will describe how you use this for governing equation discovery. So before that, I will describe one popular method. Maybe many of you already know this, but I'll describe this anyway. So this is Cindy for governing equation, as for sparse discovery of governing equations. So the idea is that you're given some trajectory for which you'd want to discover the governing equation. This could be the Lorentz system, for instance. What you do then is you estimate derivatives of this trajectory by some, let's say, some numerical differentiation method. And then you set up your linear model, which basically means that you have some basis functions. In this case, let's say the polynomial basis functions. So you have the constant 1, you have xt, you have polynomials of up to degree 3. And on the left-hand side, you want to approximate the derivative that you estimated. And then you do linear regression to estimate the coefficients. But because you want sparse coefficients, you repeat this, you threshold the small coefficients, and you repeat it a few times. And at the end, you get a sparse differential equation that is supposed to represent the system. So I guess that's shown in this picture. You have the Lorentz system, you have some basis functions, and you want a sparse set of coefficients that allow you to represent the dynamics. So there are some limitations of this model. The first one is that this is linear in the parameters. So if you look at the parameters C here, so it's linear in the C1, C up to C in the CIs. This limits modeling capacity. Another limitation is that derivatives are numerically computed on the data, which means that it becomes susceptible to noise. An advantage of this method, although, is that this is very fast, or because it just uses some linear regression. Okay, so what about our discovery model? So the way this works is, so you're given some, let's say, once again, some trajectory data. So what you do is you get some parameters that you want to that will represent your dynamics. And you build an expression. So this is similar to Cindy. This would form, let's say, the right-hand side of the differential equation. And so the difference is that this can be any arbitrary differentiable expression. In Cindy, this is limited to being a linear in the parameters. In our case, this can be any arbitrary differentiable expression, and we yeah, you can build this in order differentiation libraries like PyTorch. So this is, let's say, a simple linear combination of basis functions. You can get more complex nonlinear expressions. So for instance, so you have a tan h of some linear term, and you have a polynomial term in the denominator. So it's a more complex term that this cannot be represented as a linear combination of basis functions. So you can, in our model, you can use such terms. So the basic procedure is, once again, you get some data, you build some transformed, you get some transformation of the data, and you use the transformed data to build the expression that would be the right-hand side of the differential equation in this case. And then you're going to solve this the representation that you get for the differential equation. Now, the reason you transform the input is that we have a linear solver. Now, to do nonlinear equations with a linear solver, we can use learning. So what we do is that we transform the data, we build the expression using the transformations, but in the loss function, we will specify that the u tilde and the u's are related somehow. So, so we will have a learning procedure, and that learning procedure allows us to use a linear solver to solve nonlinear equations. So, so that's the basic procedure then. So you get some data, you transform the inputs, you build the differential equation representation. You will solve this using our differentiable solver. You will compute the loss function, maybe include a regularization term. And do you do this optimization, you will get the parameters, and that will specify the governing equation for the data. Right. So what are the some features of this? So first, this allows arbitrary differentiable expressions rather than just simply generalized linear functions that are a feature of SIMD. The other thing is that derivatives are computed in the solver rather than derivatives that are numerically computed over directly the data. The disadvantage is that this has a slower iterative optimization of neural networks rather than fast linear regression. Another, I guess, limitation or feature right now is that the expression tree structure is fixed. However, you can include any arbitrary differentiable expression there. So you can include neural networks, you can include interpretable functions, you can make it as simple as possible or as complex as possible. So, so I'll illustrate with one example. So this is I'll take this the equation that is used in rheology for non-Newtonian fluids. So what a rheologist does is, I'm told, they measure fluid properties by shear tests. You have you apply a shear force to your fluid, and then you find. You want to find the relation between the shear stress and strain for non-Newtonian fluids. And one equation, a constitutive equation for this relationship is the Kamani equation. So basically what you're given is the shear force, which in this case is given by gamma. This could be just a sinusoidal function. You get the strain, which is represented here by sigma, and then you have some parameters that I guess depend on your application. For us, what is interesting here is that this is so the equation has some more complex terms that that cannot be solved or represented as linear combinations of basis functions. So, for instance, you have the derivative of the shear force is raised to an exponent. You have, for instance, the derivative in the denominator. Yeah, so this means that if you can't represent this with fixed basis functions. If you want to recover all parameters, then you need adaptive basis functions. So this means that methods like SIND cannot be used to recover all of the parameters. So what you can do in that case is that if you know some of the parameters, for instance, if you know the exponent here, if you know, so let's say n-1, and maybe you know the exponent of the, you know that it's in the denominator, it's an exponent of -1, then perhaps you can do this. Otherwise, this is not representable in the model of SIND. However, the problem is that if you use adaptive basis functions, then identifiability is not certain. If with fixed basis functions from classical system amplification theory, you can show that you can identify the coefficients. However, perhaps we can do this. We can partially do this. So I'll show some results for this case. So we're given the shear input and the trajectories. We're given the data. So we will build the expressions. So we're given these parameters. Then we'll solve the equation to find the parameters. And we will do this with three models. One, we will fix the exponents, which means that we don't have adaptive basis functions, and we assume that we have the correct exponents. Then we will let the exponents themselves be differentiable. In that case, we will see that we get partial recovery, whereas for the fixed exponents, we get exact recovery. And then we can also replace some of the terms with neural networks. In that case, you do get some equation, but identifiability is open to question. So here's an example. So what I do in this case is I fix the exponents, for instance. So you have gamma prime, that's the derivative of the shear force. So I fix them to the true exponents. And then when I solve this, on the left-hand side is given the true trajectory. On the right-hand side is I simulate what I learned. And within a few iterations, it can find in this case, the exact parameters, excluding the ones that are already given, which are the ground truth exponents. So that's the I guess recovery for, or exact recovery for the Kamani equation parameters. Okay, next, suppose we also want to find the exponents. As I mentioned, you can't do this sort of thing with SIND because you can't have adaptive basis functions there. But because in our model, we can have arbitrary differential equations or differentiable expressions, we can learn the exponents as well. So we do this. So in this case, we let the exponents vary as well. So these are the exponents of the derivative of the shear force. Now, if you compare them with the ground truth, so in the Kamani equation, this is for instance for the second derivative of the shear force, this exponent, the second the second term, the exponent is -1 because it's in the denominator. Similarly, for the derivative of the strain, this exponent, so it recovers these exponents correctly, but some of the other coefficients are now either underdetermined or overdetermined.
Adeel, I have a question.
Yes, of course.
So in this case, you give the lambda and the sigma as the input to the network, and it predicts a bunch of different coefficients, shifts, and the exponents, and then you solve it, update the weights of the network, and do this iteratively. Is that what you're doing?
Yeah, exactly. Yes.
Thank you. I just want to confirm. Thanks.
Yeah, exactly. So yes. So just to reiterate, so what we're given is the trajectory data. So we're given the data on the let's say on the left-hand side. What we really want to find are the coefficients of the Kamani equation. So what we do is we take the trajectory, and I guess the shear input, we build the expression, and then using our differentiable solvers, we iterate through the optimization. So as I mentioned, if you have now adaptive basis functions, identifiability is less certain. even though the data matches exactly. But you identify some of the coefficients correctly. Some of them are set to some other values. So you get some sort of partial identifiability. Now, in this case, we had to assume that we know the form of the of some of the terms. For instance, in this case, we assume that you have lambda prime and it is raised to some exponent, and it is multiplied by some coefficient. So we had to assume this. So what if perhaps we know some of these terms, but some other terms we don't know? Can we just predict the unknown terms with neural networks? So yeah, we can do that. So what we do is, let's say in this case, what I do is I just replace one of the terms with a neural network function. It's just a 1D function that I apply to each time step individually. So given I guess in this case, the derivative of the input lambda prime, I compute the neural network function, and I plug this into the expression. So once again, remember, because our expression can be arbitrary differentiable functions, plugging in neural networks is no problem. Whereas for an approach like SIMD, this would not be possible. Maybe there are some extensions of that, but because we have a differentiable solver, so the whole thing can be a computation graph, and you can plug in as arbitrarily complex expressions. So just one comment on the results. So the first four. So if you look in the legend, so the different curves are you have different amplitudes for the shear force. So the shear force is some sinusoidal function, and you have different amplitudes for that. So the first four are in distribution, and the last two, if you look at the legend, they are actually out of distribution. It means that they're outside the range over which the neural network was trained. So if you look at the input closely, or the plot closely, you see a little bump over here for the last two plots. I assume this is because that the neural network has limited generalization when you query the network outside of its domain over which it was trained. So you get a slight bump. So the match for those is not exact. However, for the in distribution ones, it's quite close. All right. So yeah. So I include this example to show some of the features of this discovery method. Right. So another feature is that you can condition the parameters of the differential equation on the data. What this means is that for now, what we had was we had one equation and one type of data governed by that equation, meaning that that the ground truth parameters were fixed for the data. But now suppose we have a data set with varying coefficients. Each data set perhaps has the same equation, but with, let's say, with varying parameters. So what can you do in this case? So one approach is to, well, retrain the method for each trajectory. But because our method is fully differentiable, what we can do is that we can simply condition the parameters. In this case, this the box that says basis parameters on the neural network itself. So you see an arrow that goes from the encoder to the basis parameters, which means that now the basis or the I call this basis, but this is really just the parameters of the expression. The parameters depend on the data itself. So if you have, let's say, different data that corresponds to different, slightly different variations of the parameters, you can compute the parameters from the data, and so you can handle the variations directly based on the data. So if you were to train such a model, and assume you get successful training, so during inference, all you would need to do is to give in a trajectory, and the neural network or whatever whatever network you use here will directly give you the parameters that it thinks correspond to that that trajectory. So that would be a generalization of the parameter prediction problem. So, so in that case, you would not. So in that case, you would not need to do training on the parameters. However, because we just do this unsupervised anyway, you could still improve the parameters by test time training. So I show you some small example of this. This is a very simple example. I take the logistic equation. So there are two parameters, in this case, R, and I use the ratio R over K. So the two parameters R and K, but I predict R and R over K. So the idea is that I take a data set with sort of noisy values of R and R over K, or noisy values of R and K. I get trajectories that correspond to such values. Then I learn this model with condition parameters, meaning the parameters, the thing or the network that predicts the R and K depends on the data. And then just at test time, I just look at the values. So so it's not completely random. It shows how it is correlated with the true parameters. You can improve this by doing test time training. So I just wanted to include this to show another example of this. I have not developed this approach further, but yeah, I mean, this is something that you can do if you're interested. Okay, so then some more prediction results. You can, of course, do the Lorentz system. You can also do this with Cindy. You can do this because the right-hand side is a linear combination of parameters, and you can do this sort of thing with Cindy. However, if the right-hand side is, let's say a nonlinear function, let's say in this case of a linear combination, so you have a linear term, but then you have a nonlinear function, this cannot be represented by Cindy because this is nonlinear in the parameters. However, you can represent this in our model. You can also do time-dependent ODEs. We have the Riccati equation, for instance, and the Euler equation. Both are nonlinear in the parameters. And I plot slope fields for the discovered architectures, the discovered models. Right. So so this was ODEs. So I also mentioned that we have a PDE model, so we can also do PDE discovery. So so in this in our ICML paper, we do PDE discovery for a number of equations. We have let's say the diffusion equation, Berger's equation, the reaction diffusion equations, and a simple Navier-Stokes dataset. And we also have the porous medium equation. So so this is, I include this specifically because this I include this in the paper because this has a nonlinear term in the coefficient. So so we compare with PDE find and Cindy. Both are Cindy type methods. And we also look at how prediction under noisy settings. And we use the true positivity ratio, which is essentially how many terms are correctly found, and E infinity, which is the maximum relative error in the coefficients as our metrics. So there's some simple examples. This is not the full one that I used in the paper, but a sort of a simpler setting in which I use fewer basis functions for diffusion and Berger's equations. So I use 3 terms in the for each of these for the first derivative and second derivative terms. And you can do discovery in noisy settings as well, with some error, of course, but you can do that. So you can also do harder reaction diffusion equations. So this, for instance, is so reaction diffusion equations are a model for in this case morphogenesis, just proposed by Alan Turing. So I produced this data set using the Basilisk solver, and for this, because this is a larger data set, we have to use a more efficient solver. I'll mention that later, but we can recover the exact equation in this case. And we do fairly well in noisy settings as well. However, if you try to do this with Cindy, I was not able to make this work with Cindy. For a simpler reaction diffusion equation, for instance, this spiral data set, Cindy does work. However, for the more complex one, I could not get good result with Cindy. So here's a comparison in noisy settings. So for the easy reaction diffusion data set, Cindy also does well. For the more complicated one, it does not work. For the other cases, for burgers and for the viscous and inviscid burgers, both methods work fine. Right. So, and for the Navier-Stokes data set, also Cindy failed to get any decent performance. We do fairly well, but however, we do get some extra terms in this Navier-Stokes data set. So you can find the correct terms, but we also have some extra terms. So you get a slightly slightly lower metric. Right, so this was discovery. You can also use this ODE representation approach for prediction. So I'll just mention a few examples. We can do ODE representation for dynamics prediction and for PDE solving. So for PDE solving, by this I mean the neural surrogate type PDE solving, where you have a supervised problem, you're given some initial condition or initial time step, and you want to predict into the future. So in this case, what we do is we simply represent each point, or maybe a downsample version, as an ODE. So you have a set of ODEs, and then you solve the ODEs forward in time. So so I show one example for the KDV equation. And in this case, we can match other neural operator methods. We can also do trajectory prediction. So in this case, I take data from the JPL Horizon database. So this is data for planetary trajectories. So we take the largest, I think, 25 bodies in the solar system, and we take the trajectories from, I think, from 1980 to for a few decades. And then we just divide the data into train and test, and then we try to predict into the future. And we compare against neural ODE methods. And neural ODE methods do not work well in my experience for this case, whereas we do fairly well. I think this can be improved if you use better neural networks, but we do fairly well in this prediction method. Right. So another example of prediction is in biology, where you can use ODE representations for cellular dynamics. So this is recent work with a student in our lab. So the problem is that you want to predict cellular fate. So what that means is that cells, they start in some state, let's say they're stem cells, and then they evolve into, or they differentiate into some differentiated cells. The question is whether you can predict this evolution using gene expression data. So you're given gene expression data over a number of days. But you have some missing days in between. So can you predict the trajectory in these missing days? So that's the problem. So the interesting feature, or the different feature of this problem, is that you don't get trajectories. What you get is snapshots, because what happens is when you measure cells, is that cells die, and then you can't get a trajectory for that cell. So what you get is a distribution of states at each, let's say, day, and then you have missing days. So you don't get trajectories. So so in this case, we used a distribution loss to train the system. So this is slightly different from the approach that I mentioned before, because in this case we don't use a differentiable solver. We use we solve this analytically. We predict the the matrix A, and then we just solve this analytically. But the idea is the same, that we have differential equation representations representing data, and we can compare it against neural ODE methods, and we do much better than the neural ODE methods, and this is also more interpretable. Another application is in causal dynamics, where ODE representations are used for causal parameter discovery. So this is not my work, but work done in our lab, but it uses my method. Essentially, what you do is you take true trajectories which share a parameter, and then you can use causal representation learning results to show that this is recoverable, and then you develop a method to translating causal representation learning methods to dynamics. You can show that you can recover some shared parameters. And they show some applications in climate science for sea surface temperature and wind speed. Right. So let just see how much time I have. Okay, so I'll just explain this quickly. So I skipped this part. So how do you do this? Do the solving? So because that's the most important, I guess, component of this architecture. So so that's the red box here. That's the solver. So you're given an ODE representation, and now you want to solve this, and you want to solve this efficiently. And so it has to be GPU capable. It has to be batch parallel. So you have to be able to batch this, and you need to be able to solve different equations. So what is I guess to our advantage is that we only have linear equations. So we don't have arbitrary differential equations. So which means that we can use specialized methods for solving this. And so the approach that we take is of constraint optimization. So we reduce the problem of solving this linear ODE into a constraint optimization formulation. So basically what this means is that first, given the ODE, we discretize this over a grid. That means that we need the coefficients. These are output by the neural network. So these will be the C and the B. We have some step sizes. These can also be differentiable. And not mentioned here are also initial conditions. So what we do is that we write a constraint optimization program, and we write the constraints, and then we solve the constraints. So basically, what that means is that we have a grid, let's say n steps. We have constraints for specifying the equation. We have constraints for specifying the initial conditions. And then because our data is going to be output by neural networks, we want to impose some sort of smoothness. So we use Taylor expansions to impose that the solution that we get is going to be smooth. I won't go into the detail of this. I can answer later if there are any questions. But so these are all the constraints. You can also add some extra central difference in constraints, but yeah, that's the general approach. So you get a constraint optimization problem, and then what you get is that you collect the constraint into a matrix, the variables, and let's say Z, and the right-hand side into Z, into D, and you want to solve AZ equals D. So this is a rectangular system. So you can solve the normal equations. So you can use least squares to solve these equations. However, because we want to differentiate through these, we also want the dual variables. So we solve a saddle point formulation of the least squares problem. So you can also think of this as solving the KKT conditions for a quadratic program. So in the forward pass, we solve for Z using the KKT optimality conditions, and the backward pass, we obtain the gradients relative to A and to D. So the matrix A and the vector D using the implicit function theorem. So these are the so essentially it boils down to solving these linear systems. So there's the first one in the forward pass and the second one in the backward pass. So for large systems, the matrix is sparse. And so for larger grids, we also develop a sparse iterative solver with using conjugate gradient. In further work, we also developed an auto differentiation solver using Cholesky decompositions. So you can look this paper if you're interested. And finally, for large PDEs, we also develop a multi-grid precondition solver for use with 2D data when it's large. For instance, for the reaction diffusion equations, we use this multi-grid solver. So it's basically developing a preconditioner that is used with the FGMRS iterative solver. And it's also sparse, so you can scale this. So so this is last slide. So we have had a number of solvers now implemented. So for ODEs, we can do dense Cholesky. We can also do sparse iterative conjugate gradient. We also have a version of autodiff Cholesky. We also for PDEs, we also have a dense Cholesky method and a multigrid method. And recently, I also started using the NVIDIA direct sparse solving library. So this is also useful. Anyway, so you can look at these up if you're interested. Anyway, so that's the conclusion. So I presented our work on mechanistic networks. So that can model mechanisms in their representations, which are differential equations in this case. So this allows applications in scientific machine learning, both forecasting and discovery. For this, you need to implement GPU-capable batch parallel solvers, and doing that efficiently is critical. And I also demonstrated a specialized discovery architecture for modeling. Right, that's it. There's some references if you're interested. But thank you.
Thank you, Adeel, for presenting your work. We can now open the floor for questions. If anyone has questions for the speaker.
I have a question. Can I ask you a bit more about the sparse solvers? Is that, did you say, is this in PyTorch or what is this in?
So it depends. For instance, so there's lots of them. So the iterative conjugate gradient I implemented in PyTorch, the Cholesky, you can do this in PyTorch, but you don't differentiate through this in the first case. So you have to use the Kekulé conditions that I mentioned before, because yeah. So if you want to do the sparse conjugate gradient, yes, I implemented this in PyTorch. Yeah, I mean, so it's a bit slow because of that. The autodiff Cholesky, so what this does, so the third one, what it does is that it sort of reformulates the problem into sort of a block diagonal form. So you can just do it sort of a sequential Cholesky of the blocks. So you don't have to worry about sparsity in this case. And so you can do this in auto differentiation. For PDEs, for 1D problems, you can use dense Cholesky. It sort of works. For 2D problems, it doesn't work because it's too big. So for that, I use a multigrid approach. I use some features from CuPy for this. So some features are missing. So, but yeah, the rest is in PyTorch.
For the GRS, what's the biggest system that you solved?
I think it's 256 by 256. However, so I should mention, so because we do learning, so we don't have to solve in one go. We can sort of batch the system. We can chunk the input or the domain, and we can solve in batch. So you combine this with learning, and that's why you can do smaller I guess domains.
Understood. Thank you.
Yep. But and the last one, so this is so you have to interface with C++. So I haven't made the code public yet, but hope to do this soon for the NVIDIA CUDSS. So this is a direct sparse solver that works on GPU.
All right. Thank you. Thank you, Nat, for the question. Do we have any other questions for the speaker? I have one more question actually. For the PDE discovery, if I understood correctly, you are discovering the coefficients of the terms. Like just like in Cindy, you assume like a bunch of candidate terms and you estimate the coefficient of these terms, right?
Yes, yes.
So why didn't Cindy work for some of the problems?
So the problem is that it's too rigid, I would say. So for instance, if you if I could go back to my so what we do is that we have this neural network in between. So given the data, you transform the data, and then you don't solve the equation directly on the data itself. So and the neural network allows you to be flexible. So you can do this iterative optimization to the minimum. So I think that's one part. The other part is that if you have noise, then the derivative computations can be they can be bad.
All right. Okay, thank you.
I have one question.
Yep.
So maybe let us discuss about the case where you were saying that we have the exponents fixed. Let us say we know the exponents and we are trying to predict only the coefficients.
Mhm.
So in that case, are you giving the coefficients? Are you giving the exponential terms as an input to the neural network, or is it something that is embedded or constrained while you are building the architecture?
So you're talking about this case, right?
Right.
Yeah, or the fixed case, right? So
The
this is
fixed
one.
case.
Yeah. So
this one.
this is I just give the ground truth one. So I have the ground truth. So I just give them. So so when you build the expression, you have let's say the input, which is lambda prime. So building the expression, I just give them in the ground truth values in the exponents.
Okay, right.
Yeah.
So how are we training the model? So in the last term, do we have an additional reconstruction term for the loss corresponding to the reconstruction of the RHS of the ODE?
Yes. So what you do is you build your ODE, you solve this to get, let's say, the solution and your let's say derivatives, whatever you get. And then you compute the loss. So the loss says that, well, the solution should match the data. So that's the reconstruction term. But it also says that the transformation that we did, so this transformation here,
Right.
this should also at the end match the data.
Okay.
Because we at the end we want the expression to be a differential equation over the data, not over the transformed data. So those are the two terms
I see.
Yeah.
Okay. And also, could you elaborate upon why do we need the transform? Because I think you're also trying to impose the constraint again, saying that the transformation should be same as the input X.
Yeah, so you can think of this as not a constraint, but as sort of an annealing term. So because it's an iterative optimization, you can be very far from the solution initially, and then there might not be a solution there for the actual data. But so you want a path from your initialization to the final solution, but there might not be a path with using the actual data.
Right.
So you can think of this as an annealing term.
Okay. So do you consider it to be like probably going to some latent space and then reformulating the problem there in a way?
Well, it could be, but it's not latent. I mean, I would have to say that. I guess you could say that it's reformulating somehow. So it's sort of I wouldn't say it's latent just yet. In this case at least, for the discovery case, we do have latent representation in the prediction case, because I mean that's the whole point. We have ODE representation, so these are latent ODEs. So
Okay. And in general, how is the performance where you don't have a prior information about both the coefficients as well as the exponents? The case where you were using neural networks for predicting the basis functions too.
Well, performance is okay. I mean, but how do you measure this? So because now you don't get identifiability. So I mean, you get an equation,
Right.
So you get an equation. It's an explicit equation, almost explicit because you have a neural network term, but it's still a function. It's a 1D function, because so you apply the neural network at each time point. That's how I made this. So you get
Right.
an explicit equation. It's not the ground truth one because you don't get identifiability now.
Right.
So yeah, but it's an equation. You can use it in some domain. But yeah, it may not be the true one that you started your data with.
Okay, right. I think within the training regime, it still looks quite
Yeah.
similar to the ground truth. Yeah.
Yeah.
Oh, okay. Yep. Thank you.
I have another follow-up question. So when you solve the ODE or the PDE after estimating the parameters, do you also have to store the gradients through the solving in time part? You need to do that, right?
We don't solve through time. So we have a time grid. So
Right.
it doesn't go iteratively over time. So what it does is that, well, what you have is this whole grid. So you have to specify what grid size you want to solve on. So you write the constraints and it will solve the equation over the whole grid in one go. So yeah, so there's no iteration. So that's one difference from classical solving, because we only have linear equations, right? So we can do this. We can do this.
Yes.
Yeah.
So, but if you have a nonlinear, you need to go with the
no. So if you have nonlinear equations, we have to combine this with learning. So because so what we do is so if we have nonlinear, for instance, I don't know. Let's see. Yeah, so if you have a nonlinear term, so what we do is that we transform, let's say we can compute this, let's say x tilde square. Now this is a nonlinear term. So what we do is that at the end we say that, well, we should match the x tilde should match x in the end. So that's how we can use a linear solver, but also do nonlinear equations.
Okay, thank you. Do we have any more questions for Adeel? If not, I would like to thank Adeel again for spending his time and presenting his work at our current seminars. And with this, I'd like to close this week's session and hope all of you have a good weekend ahead. Thank you. Thank you, Adeel.
Thank you very much.
Your work.